Hello, everyone. Today, we are going to talk about the remaining parts of the Project 3 virtual memory. So largely, there are four things we should do today. First is swapping and growing stack, mmap, and lastly, we will talk about accessing user memory. So first, there are some change of plan. So there are no lab session on next week, November 15th. So this is going to be our last lab session of the semester. First part we will talk about is about swapping. There are largely three things you should do in this part. So first, you should implement the data structure to represent physical page frame. Second, you should implement page replacement policy, such as LRU, clock algorithm, or second chance algorithm. Lastly, you should implement the actual swapping itself. So you should store victim pages in subspace when they belong to the data segment or stack segment, and swap out pages should be reloaded into the memory when they are needed. So in the real OS, the page table manipulation is done with the hardware support. So you should focus on the two bits of the page table entry here. So first is 30-bit, and the second one is access bit. The 30-bit of the page table is set to 1 by hardware in the real OS when writing to the memory space, and the access bit in the page table is set to 1 by hardware each time when the page is referenced. So access bit means the page is only accessed, so by read operation or something like that. And 30-bit means the content of the page is actually changed. So when the page with the 30-bit one is selected as a victim by your victim selection algorithm, the changes must be always stored on the disk. And note that the hardware does not regenerate the access bit, so this should be done by the software or kernel program. Unlike their OS, you should manage this 30-bit and access bit by yourself in Pintos. So there are 4 page table manipulation functions provided already. It is already provided in Pintos, and you can find it on userproc/pagedr.c. So there are the first function is pagedr is 30. So it returns whether the 30-bit of the page is set or not. And you should actually set the 30-bit by yourself by using the second function. And there's a corresponding functions for the access bit as well. And start page, this is important data structure you should implement in Pintos. So think about when you're running out of the physical memory space, and you should select a victim for replacement. So you should actually select which page you should kick out to the disk. So for that, this data structure is needed. So this data structure represents each feature page that contains the user page. Here, user page means the virtual page you implemented in the last lab session, and it contains some elements here. First is physical address of the page. Second, reference the virtual page object to which physical page is mapped. And third, reference to the thread structure to which it belongs. First one is LRU, which is the field for the list. I'll talk about it later. And this structure is not implemented. There are no predefined one for this structure in the Pintos, so you should make this structure by yourself in this path. So here the element should be the one I introduced here. And you can add anything you want if you think it is needed. So this is how this structure page is used in the Pintos. So you should manage vehicle pages in use as a list of pages. So here you can see the LLE list. This is a global variable reference to the list of pages, and each page is linked to each other. In the figure, it looks like the data structure for managing the pages are linked list, but this is not fixed. So you can use any data structure you think that is efficient for managing the pages. You can use hash table or like advanced data structure if you think that is necessary for make this process more efficient. So as I mentioned before, each page structure includes the thread, reference to thread structure, and corresponding virtual memory entry, and other things you will need for this project. So when you are actually swapping out the page, you should first select the victim page in the list of the pages. And if it's dirty, you should write it to the disk. And finally, you should also clear the page table. So in the Pinterest, sub partition is managed per sub slot unit, like the page. It is 4 kilobyte per each slot unit. So in Pinterest, the sub partition is maintained by a sub bitmap, which is a global variable in memory. So you should search the bitmap for free slot. So here is a figure for that. So you can see there's a sub bitmap, and this 0 means the actual sub partition for this sub is free, and 1 is it's in use. So actually, this is an important question. So what happens to sub bitmap if the system crashes? So this sub bitmap is managed on the memory. So if the system crashes or the contents in the memory is gone, so this sub bitmap will be gone as well. So in that case, we don't know which sub partition is used or not. So we don't know whether this slot is free or not, which means our data in the sub partition is gone. So this is the functions for the BiPinterest for subspace manipulation. So subspace is provided as a block device in Pinterest. So there are four block devices in Pinterest. The first is block kernel, which is the OS partition. Second is block file system. This is a file system section. And the block scratch, and the final one is swap partition. So if you enter this block swap into this function, you'll get the pointer to the block device. So you can use this block device to read the contents at the block, or you can write to the block with these functions. So for the implementation of the swapping, you should do first, you should implement the LLU list for physical page frame. So it is the list of struct page. And as I mentioned before, you can use any data structure you want for managing the list of struct page. Yeah, so it would be the list of physical pages allocated to the user process. And you should implement functions for allocate and release physical page frame from the list. So when there are no more physical page frame available, you should select a victim by your algorithm like LLU or second chance, and you should sub it up and reload the demanded page. And you should modify page fault handler for swapping. So before you implement this swapping, physical page is allocated directly when the page fault occurs, but when there is no page to allocate, Pinterest is just finished. But after you implement this swapping, physical page is allocated from the LLU list when the page fault occurs. And when there is no page to allocate, Pinterest will swap in the page and kick out the victim to the subspace or file system. So these are functions you should write for swapping. So you should write a function about error list initializing insert to the array list and remove it. And you should write a function to allocate a page from array list and free page from the array list. And you should also implement the function to select victim page and sub out the page. So you can use whatever algorithm you want to select the victim page. The examples are like clock algorithm or second chance algorithm. And finally, you should write a function about swapping itself. So initializing and sub in and out. These are the functions you should modify in this section, the swapping section. So first is handle the page fault. So you should modify the function to allocate physical pages from your array list when the page fault occurs. And you should also implement the change its function to modify to sub in VM entry if the VM entry type is VM anonymous. So this is going to be heap or stack pages. And you should modify the setup stack function. So you should modify to allocate pages from the array list when page fault occurs. And finally, in the main function, you should initialize your own array list, the global variable. So to allocate and free the page, you will until now you will just use the pallocate page function, and when the Pinterest is running out of page, the Pinterest is just finished. But now, when you get no or zero from the pallocate page, if it's not successful, you should swap out the victim page and do it again to get a new free page. And also you should add using page to array list, and return the page. And likewise, when you free the page, you should find the page in the array list, and you should delete it from it, and you'll call this function. And this is a detail of the swap out. So you should do the different thing according to the type of the page. So there is a binary page and file page and anonymous page. Or the binary page, if the dirty bit is 1, you should write it to the soft partition and free the page frame. So this means the code of the process is actually changed by the user. So for swapping in, you should change the type to the VM anonymous page or demand page. Else, the demand paging, if you don't change the type to the VM anonymous, the demand paging will just bring the unchanged code from the file system or disk. Second, for the files, if the dirty bit is 1, you should write the page to the file itself. So you should not write it to the soft space, but you should just write directly to the file and free the page frame. If the dirty bit is 0, you should just free the page frame. For anonymous pages like stack or heap, you should write to the subpartition. And when you're swapping out the page, you should mark the page not present in the page directory, using this function. So this is a changed version of handling page fault for anonymous page. So you should first check whether it is binary file. If it is, you should just load the data to the memory from the file. And if it's not, you should find, if it is so anonymous page, you should just bring the page from the subspace. So yeah, this is the function version of what I said before. So in case of VM anonymous page, you should implement the swap in code. Yeah. The second part we are going to talk about is growing stack. So until now, the stick size of the Pintos is fixed to 4 kilobyte. So in this section, you should make it expandable. So when we expand the stack, so if a process accesses the address that lies outside the stack, and that can be handled by the expanding stack, you should expand the stack. So we will consider the legitimate access to the stack is accessing address is less than the stack pointer minus 32. So in that case, you expand the stack. And the limit of the stack size is 8 megabyte. So I'll talk more about that. So we will consider the user is accessing stack in the right way when the accessing address is within the 32 byte of the stack top. This is because push A instruction in your architecture pushes 32 bytes to the stack at once. So if you access the stack like 32 byte of the stack top, we will consider this access as a legitimate access, and we will grow the stack correspondingly. So this is a page fault handler with a consideration of stack extension. So this part is added. So yeah, when the address access is legitimate, you should grow the stack. Third one is memory map file. So this is the explanation about MM and M on map. So as you can see in this code, when you open a file and you want to map this file directly into the disk memory version of user process address space. So here the address is this. So we can map the file into the user's memory space using this mmap function. So this is a file descriptor, and this is a pointer to the data section. So what it does is you just directly map this file content into this memory address space. So when you change the content of the memory space here, it is directly reflected to the file content. So you can change the file content by just change the memory content here. And you can unmap this map. So you to unmap this portion. So like I said, mmap function maps the file content into the process virtual address. So if the file is more than 4 kilobyte, and then the file content will be separated into multiple pages here. So in this case, the file size would be like between 8 kilobyte and 12 kilobyte. So then you should make a frame entry here by divide. So each page, you should make each page for that. And you should enter these pages into the virtual page pool. This is what you learned from the last lab session. So yeah, you should insert these VM entries into the virtual memory hash table. And this is the detailed explanation about mmap function. So mmap function load file data into memory by demand paging, and mmap page is swapped out to its original location in the file. So mmap page, if the mmap page is selected as a victim page, it should not write it to the swap space, but just in the original location in the file. And for the fragment pages, like let's say the file size is 10 kilobyte, then the 2 kilobyte of the last page would not be used. If so, you should just fill the unused fraction of the page with 0. And this function returns mapping ID, which is a unique ID within a process to identify the mapped file. And mmap fails if the file size is 0, address is not page aligned, address is already in use, address is 0, and finally, standard input and output are not mappable. So file descriptor 0 and 1 is not mappable. And n unmap the mapping in the mmap list, which has not been previously unmapped. So requirements of the mmap is like this. So all mappings of a process are implicitly unmapped when the process exits. And when a mapping is unmapped, the pages are written back to the file, not the swap space. And upon unmapped, the pages are removed from the process's virtual page list. And once created, mapping is valid until it is unmapped, regardless of the file is closed or deleted. So when you map the file into the using mmap, and if you delete the file, the map is still valid. And finally, if the two or more processes map the same file, they do not have to see the consistent view. Which means, so let's say if there are two processes map the same file, and they modify the content by themselves. So if the content diverges, and they do not need to have to see the consistent view. So you should not care about that. And this is a new data structure and functions you should modify or create for supporting this mmap. So there is a struct mmap file. This is a data structure containing information about the map files. So it will contain mapping ID, a unique ID for the mapping, and mapping to the file object, and the list of element, and the virtual page entry for the file. And you should also change the page fault handler to support mmap. And upon the process exit, you should release all VM entry corresponding to the mapping list and the end of the process. So in the thread structure, you will make a new element named mmap list, and mmap list will reference to the list of mmapped files. So as I said, like the page, you can use any data structure for this list, and each mmap file is referencing their virtual pages for the file. And here, this part is added in the page fault handler. So if the type is VM file, which means mmap files, you should load the data from the file to the memory. And finally, I'll talk about accessing user address space. So thinking about this scenario, so in the user context, user call the system call read to read their important data to their buffer, and it will make a context switch to the kernel context, and the kernel will execute the read system call, and it'll read the data from the disk. And let's say the content is recorded in the page A, which is a physical page, and then it will write the data to user buffer. And during the reading from the disk, let's say another context switch happens. So other process requires something, and let's say the context switch happened by the page fault. So to handle the page fault, and let's say there is no available physical page, so it'll select a victim page. And let's assume that page A, which was the kernel, is already doing something on that page, but it is selected as a victim. And the kernel will write a victim page, the source space, and then it recovers from the interrupt handler. And if it continues to reading the page A, so it brings the content from the disk to page A, and the content of the page A will be corrupted. So it is not the same content the user required. So to prevent this from happening, you should prevent evicting the pages accessed during the system call. So when the system call is doing something on the physical page, you should define a pinning flag about each physical page and prevent it from evicting. So in detail, on every system call, you should find the virtual page that is affected by the system call and pin the associated physical page. So after the system call returns and before the system call handler returns, and you should unpin the pages, And on the swapping handler, you should not select the pinned pages as a victim. Yeah, so that is required to protect the content of the page from corrupted, from the corruption. So project 3 is the due date of the project 3 is November 28th. And as you know, there will be a lot of randomness in this project. So we will grade 10 times and give you the average score of it. I really recommend you to start this project early, because I remember when I did the Pintos before, my code fails the test case every 3,000 tries. So there's a lot of randomness in this project. So start early. Yeah, so this is the end of the lab session of the semester, and thank you.